might as well go ahead and start recording. Brandon Simpson.
Yes.
Put your hand up. There you go. Jory Owens, not here yet. Megan Walker. Tony Lee. Zach Woodard. Jacob Childers. Carlos Aguilar. Val. Jesus. Derek Heineman. Michael DeBach. John Caldwell. Lauren Pendergrass. Jared R. Robinson. Jacob Hoffman. Jesse Mark. And let's see.
Came in and walked back out.
Chris came and gone, huh?
He saw no Beatles this week.
Nobody that mattered anyway, huh?
Yeah.
Well, give me a flood. Anyone else come in since I started handing out? All right, who has questions? Oh, there's Chris. Wow. Bring it on. Separate you. Yesterday?
Yes. Jacob.
Sent you? Well, you will get a makeup on it.
Just want to take it out.
No, I'm giving a bonus exam out here right now. This bonus exam is essentially a rework of the one you just took. I changed the numbers, and I'm going to point out to you that on the two drawings, I put instructions under the drawings how to change the numbers in the drawings. So, hope you're paying attention right now. If you work the problem with the original numbers, you will not get credit for it. So, pay attention now so that whenever you do rework the problem, you'll use the right numbers and you'll get the right answers. Oh yeah, here you go. Got some hand back for you. This bonus exam is a take-home exam. You have until next Thursday during class to return it to me. You can come by my office and drop it off anytime between now and then. You can drop it in the mail, the little box outside my office door, or you can wait and bring it back next Thursday in class. Did I give you one? Like I said, these put instructions on the pictures how to change the numbers. Pass this back to him. Make sure you change the numbers before you work the problem. This exam will replace your lowest grade, your lowest exam score. Now, I'm already throwing out your worst grade.
You're doing both?
I'm doing both, yeah. I'm going to throw out your worst grade. This will basically replace your second worst grade. Could you get these for the back row, please? I hope it helps. Don't fail to take advantage of the opportunity to bring your grade up significantly. Now, I'm not going to work any of the problems off of the exam because, well, it would be cheap. But if you have questions about any of the problems from the exam, I will try to address your questions. Yes.
Can we get one more for Travis?
One more what?
One more for the test.
You mean you want double credit for one?
No, I was going to get one for Travis. Since Travis asked if we
Travis can come and get one from my office. Anyone who is not here, they're not going to be excluded from getting the opportunity. They're going to lose however much time it takes for them to show up to pick up the exam. I sent out emails to everyone in the class individually yesterday, letting everyone know that this was happening. So if somebody decided not to show up, then they may just lose a day to work on the exam. Or two, or the whole weekend, depending on how long it takes for them to show up to get the exam. Now, like I said, I'm not going to work the problems for you, but I will try to address any questions you had from the exam. So, speak now or forever hold your peace. Who has questions about any problems they didn't understand? Names? Kyle?
Steven?
Turner?
Yep.
Oh, that's what you look like.
Start a sign-in sheet yet?
I've started one. I don't think anyone else is cool with it. There you go. Thank you.
I see that. What do you got?
Stephen Turner.
What's the date? So I don't mess it up today. All right. I think it's fourth. Fourth.
Oh, I got more for Anthony Lee over here. Well, it's not that bad.
Pretty good.
All right, Travis Black. Did you take the exam?
I wasn't here Tuesday, no sir.
Oh, okay. Well, then I don't have anything else for you. Here we go. Stephen, I do have one of these for you. Pass this back. You can turn it in anytime between now and next Thursday. Thursday's class period. So were there really none of the problems, none of the questions on the exam that you just didn't understand how to work with?
What I struggled with is whenever I had this sides, 1 degree, like 1 angle.
Mm-hmm.
I just threw a total blank, but I couldn't figure out. I couldn't remember how to plug the numbers to find the other angles. Does that make sense?
Yeah.
That's where that was something I struggled with.
Okay. Well, then let me see how we can simplify this. We have two sides and the angle between them. Okay? Now here I'm using, in fact, I'm going to not use A, B, and C because what I want you to do is to understand the relationship that's involved here instead of trying to worry about which one goes on the bottom and which one goes on the top. You have two sides. Side 1, side 2, and an angle that is opposite, that is between them. Okay? Doesn't matter what you call each one, A, B, C, pick a letter, any letter. The point is that you know two sides and you know the angle between them. The first thing you need to know is the length of the other side. The length of side 3 squared will be equal to side 1 squared plus side 2 squared minus 2 times side 1 times side 2 times the cosine of the angle between them. So if you have two sides at an angle and that angle is between the two sides that you know the value for, this is how you find the length of the opposite side. Okay? Yes?
Draw that relationship on
Which side do you want to call side 1?
it doesn't matter, does it? Just like it's S3's opposite of theta.
Fair.
Right.
So which one would be theta between if you know side 1 and side 2? There you go. Now what if you know two sides and an angle but the angle is now opposite one of the sides you know? In other words, it's one of the other two angles, it's not the angle between them. But the first thing you have to do, when you have two sides at an angle that is not subtended between them, the first thing you have to do is find out how many solutions are you looking at. Okay? And you know this angle between these two sides, and you know the length of the side adjacent to the angle. You know the length of the side opposite the angle. What you need to know is this height. So you take the odd side, the side that is the angle, and the opposite side are the paired side and angle. You take the odd side and you multiply it by the sine of the angle, and that will tell you the height of that triangle. Megan Walker. I got handouts for you, but we'll get them out. Don't leave without picking them up. Now, once you know this, the height of this triangle, you still don't know how long this side is. You know how long this side is. The first thing you got to ask is it long enough to reach this bottom side, this other side? So if side 1 is less than h, if it's not long enough to reach the bottom of that triangle, if it's less than this height, if it's less, if the side opposite the angle is less than the side adjacent to the angle times the sine of that angle, if it's less than h, then there are no possible solutions. The other known side is too short. It won't reach. Zero solution. The next possibility is that this side is exactly equal to the height of the triangle. If it's exactly equal to this side times the sine of the angle, then that means you have one and only one possible solution, a right triangle. Okay? The next possibility is that side 1, this side, this opposite side that you know, is greater than the side next to the angle. Okay? If it's greater than this side, then you have, again, only one possible solution. It's going to be for it to come out here somewhere. Okay? You will get two solutions when the length of this side is greater than h, but less than this side. So if h is less than the opposite side, and that is less than the adjacent side, and when I use opposite and adjacent here, I'm talking about relative to the known angle. When this is true, you have two possible solutions. One where it comes here, and one where it comes here. And then you have to work out both of those possible solutions. Okay? Any questions about this? There's one other thing I want to point out to you because I tripped up a few of you. When you're solving a triangle that looks like this, I'm not saying that it belongs to any particular problem on the exam, but if you're solving a triangle that looks like this, and you want to know how tall it is, if you can determine this length, the length of that side, and you know this angle, then what is h? That's all you need. Any other information you have might help you to determine this length, might help you determine that angle, but that's it. And if you know this angle, and you know this angle, then you can determine that angle because the three of them have to sum to 180. And by the way, if you ever solve a triangle and all three of the angles add up to more or less than 180, you got it wrong. So, always think about what you're trying to determine. What's the question asking for? Find that answer. And any extraneous information that you don't need, you don't need. Now, any more questions before we get to this week's material? We got to learn all about vectors this week. Well, maybe not all about them, but we're going to learn. Did you sign in? Anybody else not sign in? We'll look at chapter 5.4 this week. Did I give you one of these? Take home? It's a bonus. Take it. Do it. Earn the points. And any of you that talked to any of the people that aren't here today, tell them to be sure and review the video on Canvas so they will have all the information they need to know what they need to do and how to do it. All right. So who can tell me what is a vector? Somebody, anybody? Did no one see Despicable Me? Seriously? No wonder you're all such sour pusses. You have seen Despicable Me. Then what is a vector?
He's the bad guy.
He is the bad guy. But why did he call himself Vector?
His name is Victor.
It was Victor and he changed it to Vector. He gave a very specific reason in the movie. Because he has both magnitude and direction. That's a vector. A vector is a quantity that not only defines a magnitude, but also a direction. Weight is a vector. Velocity is a vector. And yes, everyone hold your breath and bite down and bring a bullet to class so you'll have something to bite on. But this week we're going to learn some physics too. We're going to actually use vectors to analyze forces. Okay? Oh yes, front center. I definitely got hand backs for you. Also going to want, well, there you go. Here you go. Pass this back to Matt. You can look at the video on Canvas to find out what. All right. Vectors describe both magnitude and direction. So, what is the first thing they define? They start talking about how to add vectors geometrically. And they talk about some of the properties of them. was a vector typically depicted with an arrow that has a length and some direction. These are the two components that make up a vector. The length of the arrow that depicts it graphically is proportional to the magnitude of the vector, and the angle depicts the direction that it points in. So, they tell you here that if you have a vector that originates at a point P and terminates at a point Q, then this vector is the vector PQ. Okay, they introduced something called a zero vector. A zero vector, it's a vector that has zero magnitude and no direction. And I'm sure that that's really interesting to some mathematician somewhere. Okay, yeah, it's just what it is, so make a note, remember it. Now, two vectors are equal. Vector V is equal to vector W. Oh, and just a little side note here about my notation. In some books, you will find when a variable has a line drawn over the top of it, that means an average or a mean value. Okay? Vectors are traditionally drawn in boldface type. In case you haven't ever tried it, I can tell you from personal experience, it's very difficult to write in boldface, especially with a marker on a whiteboard. So, when I draw a letter and put a line over it, that means a vector. Okay? Just letting you know. Especially with regard to this chapter. Now, what would you think it means? What do you think would have to be true in order for this statement, this equation, to be true? Just somebody tell me off the top of your head. Guess. Brandon. What must be true in order for this statement to be true? That's it. Simple as that. Vector V and vector W are equal if and only if vector V has the same magnitude as vector W and it points in the same direction as vector W. Then they're equal. Now, we are going to learn how to add in vectors algebraically so that you can actually punch numbers into a calculator and get meaningful results. But vectors are kind of abstract for a lot of people, especially at first. So before we learn how to do it algebraically, I'm going to go through some of these terms that we're going to be using, some of these operations we're going to be doing, and show you what it means graphically. So when you talk about adding two vectors or multiplying a vector, you will understand physically what does that actually mean that you're doing. So, we're going to talk about some of the properties of vector arithmetic while we do this. Let's say this is vector V. and this is vector W. Then to add vector V and vector W means you take vector V, and then you take vector W, put the tail of it at the end point of vector V, and that is how you add them. And the two of them produce a new vector, V plus W. Everybody see how that works? Now, first thing we want to learn is that vector addition is commutative. Remember what commutative means from arithmetic? It means that V plus W is equal to W plus V. What if we did here, instead of V plus W, what if we did W plus V? You're still going to get the same resultant vector. It will have exactly the same magnitude, and it will point in exactly the same direction. It doesn't matter which you add first, or which you add to which. We also, oh, this is going to get fun. Not only is it commutative, vector addition is also associative. Oh, where do I have room to do this? Okay. That means, let's add another vector. We call it U. I've been seeing lightning since I got up at 5 o'clock this morning. All around the horizon, in every direction. Flashes after flashes after flashes, and it was starting to freak me out just a little bit because my whole commute into work, all this lightning, no thunder. It was like that movie about the War of the Worlds with Tom Cruise when the aliens kept blasting their lightning bolts on the ground, but there was no thunder associated with it. Anyway, kind of comforting to hear some thunder finally. All right. Somebody help me out. From your days in arithmetic, introduction to algebra, what does associative mean? It means U plus V plus W is equal to U plus V plus W. Again, doesn't matter which you add first, it all works out the same. So what is, graphically, if we add U plus V plus W, we've got U here. And we know what V plus W looks like. So we add V plus W to it. Which is, you'll remember, or at any rate, when we add that to U, get a hot mess. We get this vector u plus v plus w. What if we start by adding u plus v? Well, here's u, and here's v, and then to that we add w. We still get u plus v plus w. And it really doesn't matter where you put the parentheses. And since it's commutative, it doesn't really matter which order you put them in before you add the parentheses. And here's that zero vector popping up again, that if any vector v plus the zero vector equals what? Equals v. Alert the press.
He probably wrote a paper.
I bet you somebody did. Actually, there's a story behind the number zero. It's, the Arabs, the Semitic intellectuals, Egyptians, Arabs, that bunch. They, in fact, it comes from the word zero comes from the Arabic word sifr, which means zero. And it's also, I think, don't quote me on this, I think it's also where we derive the word cipher from. But it was quite the tumult when they first introduced the concept of zero to the Greeks and to the Europeans. And it was like, well, kind of like me and this stupid zero vector. It's nothing. So what do you mean? What are you talking about? It was quite took a while for them to wrap their minds around the ideas. Maybe I shouldn't make fun of the book for including the zero vector, but I do, and I'm going to continue to do so. So deal with it. The zero vector, you add zero to anything, you still get zero. In fact, zero is defined in some texts as the additive identity. You understand what that means? It means you've added to anything and the result is that thing. Just like one is the multiplicative identity. You multiply anything by one and you get that thing. And that is going to come in very handy. Hi! Ta-da! Got it?
Yes.
You want my good side? The multiplicative identity is definitely going to be important to vectors. We're going to get there not too long from now. It's called the unit vector. One final problem. We're going to talk about, and that is subtracting vectors, or the difference vector. If vector v is a vector that has magnitude and direction, what is negative v? Pilot. Right off the top of your head.
V.
If vector V, if V is a vector, what is negative V?
Opposite of a vector.
It's,
Oh, 0.
no, not the zero vector.
Dang it.
Negative V is still a vector. It's a negative vector. What is a negative vector? It is a vector that has the same magnitude, but the opposite direction. Points in 180 degrees from, or pi, from the original vector. So, if you have two vectors, V and W, then to subtract W from V, you would add negative V. So, here's V and W. How do we do that subtraction graphically? Just to make a picture of it so we understand what this means. First thing we do is we take W and we make negative W. And now we add negative W to V. And we get something that looks like this. Everybody good so far? Any questions? This is all still just conceptual stuff. And now, this is to show you how they interact when you add and subtract them, and you do it to get them in graphically, to get a picture in your mind of what you're going to end up with. But what happens when you multiply a vector by a scalar? First of all, what is a scalar? Somebody, anybody? Exactly. It scales the vector. Exactly right. A scalar is a quantity, it's a magnitude modifier, but it has no direction associated with it. So, it's just, in other words, it's just a number. So if you have a scalar alpha and a vector v, why can't they make shoes with laces that are the right length? I swear these. Now, first we need to make some assumptions. We need to specify that alpha is greater than 0. Alpha were 0, and we multiplied the vector v by alpha equals 0, what would we end up with? We end up with that 0 vector. We don't want that. Well, if we multiply alpha times the vector v, then we will end up with a vector the magnitude of which is equal to, the magnitude of the vector will be equal to the magnitude of v times alpha. And its direction will be in the original direction of v. So that's all it does. The scalar multiple just changes the length. If it's greater than 1, it makes the vector get longer. If it's less than 1, it makes the vector get shorter. Dewberry. I got handouts for you, and get with me after the lecture. Don't leave because I've got that bonus exam to give you too. All the pertinent instructions for it are on the video. On Canvas. Oh, and by the way, hoorah. All right, now, say again? All right, well, was it funny? Must not have been because he didn't laugh. All right. If alpha is greater than 1, greater than unity, then the vector b gets longer. If it's less than 1, but greater than 0, then the vector b gets shorter. It's like you would expect with any scalar multiple. What happens if alpha is less than 0? Suppose alpha is a negative number. And it makes b negative. It's exactly. It will have the magnitude of b will still be alpha times the original magnitude of v, but its direction will now be in the opposite direction. So if you wanted to bring this definition back and revisit taking the difference of two vectors, taking a negative vector, making a negative vector, all we really did was say we're multiplying it by a scalar of -1. So its length stayed the same, and its direction changed. But you don't have to leave the direction the same. If alpha is anything other than 1, then it'll have the opposite direction in the new magnitude. Told you we were going to get some physics. Who here knows the difference between mass and weight? Well, mass is a quantity of matter. Weight is mass times acceleration. On the surface of the Earth, that acceleration is due to the force of gravity. So that whatever your mass is, it will be accelerated by 9.8 meters per second squared, and that is what produces your weight. In the SI system, in the metric system, that your mass would be measured in kilograms. The acceleration would be measured in meters per second squared. And when you multiply kilograms times meters per second squared, you end up with newtons. And it's named after the scientist, not the candy bar. Okay? Although I think I kind of prefer the candy bar. But if we were working in pounds, pounds is a weight. It is your mass in the English system, in the SAE system, times 32 feet per second squared, which is the acceleration due to gravity in the English system. Does anyone know what the units of mass are in the foots and pounds in the English system? Anybody? You are going to learn something new today. If you ever find yourself in a physics class and the professor asks what is the units of mass in the English system, they're slugs. So if you you take your weight and you divide it by 32 feet per second squared, that will tell you how many slugs of mass you have. Mass is a scalar. It's quantity. It has no direction associated with it. Acceleration is a vector. It has a magnitude, which is 9.8 meters per second squared, or 32 feet per second squared. But it also has a direction. What's the direction of the acceleration due to gravity? Exactly, down. Downwards, because we're all on the surface of the earth. It's actually towards the center of whatever you're standing on. For us, that's Earth. So, since we're talking about it from a perspective of the Earth, then it would be at an angle of somebody.
180.
If that's 0, that's 90, that's 180. What's that? 270. Or you could say at minus 90 degrees. Or plus or minus pi over 2, or 3 pi over 2. The point is, however you write the angle, it should be pointing straight down. That's the magnitude and direction of that vector. In physics, that vector is given the name g, lowercase g, in specific. It's be specific, which stands for gravity. So if you weigh 65 kilograms and you have a calculator, I'm looking at you. Oh, don't put it away. We need your calculator.
You want a calculator?
Oh, that's not a calculator?
Well,
Please tell me that was a calculator.
all right. What do you need?
9.8 times 65.
637.
That would be
Oh, less. 637.
637. Twice we got 637. So if you weigh 65 kilograms, and you also, if you are 65 kilograms of mass, then you weigh 637 newtons, which should tell you something about why we use pounds. Because you think you weigh a lot in English, wait till you start counting in metric. Okay, there's a table on the top of page 346 that kind of summarizes these properties we've just talked about. All right, here's another table. Kind of already talked about it. It's talking about the properties of the magnitude of V. In your book, you will see it as two lines and the vector between them. That is the notation used in the book for the magnitude of the vector. Okay? is a v and alpha is a scalar, then the magnitude of the vector v is greater than 0 or equal to, it's always greater than or equal to 0. Okay, in other words, you can never have a negative magnitude. You can have a negative vector, but that only affects the direction, not the magnitude. It can only equal 0 if v is the 0 vector. Otherwise, it's greater than 0, always. It's always a positive magnitude. We'll also find that the magnitude of negative v is equal to the magnitude of v. And I'm going to drop the double lines because I talk about magnitudes as an absolute value. So I'm just going to, when you see me stop doing the double lines and start going back to the absolute value, understand I mean the same thing. And if alpha is a scalar, then the magnitude of alpha times the vector is equal to the magnitude of alpha times the magnitude of the vector. Okay, so even if alpha is a negative number, the magnitude of alpha times the vector is equal to the magnitude of alpha times the magnitude of the vector. And with that, oh yeah, there's one special vector that we need to talk about. And it's the vector they call u. U is the unit vector. Okay? So the magnitude of u, by definition, is 1. So if you multiply the unit vector by, if you multiply a unit vector by any scalar, you end up with a vector that is the magnitude of that scalar in the direction of the unit vector. And if you want a unit vector for any vector, then you divide the vector by the magnitude of that vector. And that, by definition, gives you a unit vector in the direction of that vector. Now, let's get into talking about how to deal with vectors algebraic, quantitatively. So we're no longer talking about drawing lines on a paper and trying to do it with accuracy. If you can, if you've got a computer graphics program and you can very accurately draw a line to a very precise length at a very precise angle, and draw another one at with the same precision and angle, and you can measure the distance between the endpoints and the direction between the endpoints, and you can come up with a very precise, graphically added vector. A whole lot easier to do if you just use numbers. So, algebraic vector, they represent it as, oh, I see, they use greater than and less than sign. When we're going to introduce some new angles now, some new brackets. Remember when we talked about this notation with the curved brace and the curved parentheses? That means the range, it's an ordered pair, x and y. We're talking about in a domain domain and range, it means the endpoints are not included. If we use square brackets, that means the endpoints are included. Well, now we're introducing another set of brackets. Less than, greater than brackets. That is an algebraic vector, xy, that is assumed by definition that it begins at the origin of a Cartesian coordinate plane. So if this is your Cartesian coordinate plane, and this is the point x, y, then the vector that begins at the origin and terminates at that point is the algebraic vector x, y. Now, what is the magnitude of x, y? Somebody, I know somebody's got this. Uh-oh. Somebody help me out here. What's the magnitude of that vector? What is the distance from the origin to the endpoint of xy? No, not infinity. Very much not infinity. Very finite. How long is it? You all have the exponential notation in algebra where you know that raising something to the power of 1/2 is the square root. Raising it to a negative exponent is the reciprocal. Never mind. Pythagorean's theorem. X squared plus y squared equals z squared or c squared. So the magnitude of xy is the square root of x squared plus y squared. What is the angle? Tangent of the angle theta is y over x. That is how you define a vector algebraically. Now remember, think back a few weeks, we looked into that whole issue of domains and ranges and inverse functions. So when you start looking for, when you start taking the inverse tangent of x and y to find the angle, it's up to you to make sure you know which quadrant you're supposed to be in, because the answer is only going to keep you in quadrant 4 or quadrant 1, from minus pi over 2 to pi over 2. If you're in 2 or 3, it's up to you to know where you're at and adjust the answer accordingly. Like I've said, your calculator will do the arithmetic great. You have to do the math. Now, this is how you define a vector algebraically, but it's awfully convenient that it happens to start at the origin. Well, what if you want to add two vectors together? Kind of hard to do algebraically when they both start at the origin, because in order to add them, you've got to move the beginning of the first one to the end of the second one, or vice versa. So, how would you define a vector algebraically if it instead of starting at the origin, it starts at some arbitrary point xy. We call it x1 and y1, and ends at another arbitrary point x2, y2. Now, what is the magnitude and direction of that vector? First thing you need to know is what is this length? Length 1. What is that length? Exactly. This is x2 minus x1. What is this length? Bingo. y2 minus y1. Now, what is the magnitude of that vector? Say again? It's the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the magnitude of the vector. What's the angle? Ratio of y2 minus y1 over x2 minus x1 gives you the tangent of the angle. Now, suppose you have two vectors. And let's say the other one starts here at x3, which is less than 0, and goes to x3, y3, and goes to x4, y4. You add these two vectors together. What do you need to do? You need to find out the length from here to here, and add it to this length from here to here. So to add these two vectors algebraically, you would add L3 plus L1 that would give you the length of the sum of the two horizontally, and its length vertically would be L2 plus L4. This length plus this length. And that would give you the vector sum of those two, or the algebraic sum of those two vectors. Believe it or not, it's not actually as hard as it it seems. It's not as complex as it seems from this explanation. And the reason it's not is because of our friend, the unit vector. How would we write this vector? Call this one V and this one W. So how would we write V using a unit vector? If we have a special unit vector, I starts here, horizontally at 0 degrees for 1 unit, then if we know this length, x2 minus x1, when we multiply it by this unit vector, which we're going to call I, I'm going to denote it with a little caret on the top, then V simply equal to x2 minus x1 times the unit vector I. And that gives us this vector right here. Plus a second vector, y2 minus y1 times a different unit vector points at 90 degrees. It's 1 unit at 90 degrees. We're going to call that one J with a caret. That gives us this vector. So that the vector V becomes the sum of those two vectors. Does everyone see that? Because remember, we're using x1 and x2 and x1, but if those are actual numbers, then that means this is just a number, alpha. y2 minus y1 is a number, beta. And you now have a vector v that's equal to alpha times the unit vector I plus beta times the unit vector j. And that is a vector in rectangular coordinate form. Here's another vector. It has this vector plus this vector. Well, this vector is x4 minus x3 times times I. x4 minus x3 we'll call what? Delta. So W now becomes delta times I. What's this one? x4 minus y4 minus y3. What's the first thing you notice about it? Pointing down. So this is a more negative number than this one. This is actually negative minus a smaller negative, so this is a negative, what's next? Gamma. Plus negative gamma times j. Well, you would just write that as delta I minus gamma j. That is your vector W. Once you have it in that form, now how do you add V and W? You just add the horizontal, the I components, and then you add the J components. So V plus W becomes alpha plus delta I plus beta minus gamma J. Sorry about that, ran out of room. And it's as simple as that. I know I'm using Greek letters, but all I'm doing that is so I don't have to keep writing x2 minus x1 and y3 minus y4. You're working a homework problem, those are all just going to be numbers. Does everyone understand how this works? One last theorem. I'll let y'all go. You don't have any questions? Any questions? Yeah.
Over here, x squared, so basically x squared plus y squared equals v squared, right?
Exactly.
Okay, so v is the square root of,
X squared plus y squared.
but over here you got x. There's no squaring with the equal to v.
That's because this is just a number.
Yeah, but that, no, but yeah, but that would actually, and
It's
x2 minus x1 would be a new x. And y plus would be a new y. So then you have x3 basically plus y3 equals v.
the magnitude of this vector would be x2 minus x1 squared plus y2 minus y1 squared, and then take the square root. That would be the magnitude of this vector. Now, what would be the magnitude of adding these two vectors? What's the magnitude of this vector v right here? Whether we write x2 minus x1 or alpha and beta, what's the magnitude of v? The magnitude of v is still the square root of the sum of the squares. Oh, well, all I'm doing is I'm saying alpha, remember, and once you put this in, once you have actual numbers, x2 and x1 aren't just going to be, they're not going to be a couple of subscripted variables, they're going to be a couple of actual numbers, coordinates on a coordinate line. So when you subtract them, you get a definite number, and I'm just calling that number alpha. In other words, alpha is x2 minus x1.
Yeah, I get that. No, but freedom of theory says you have to take that square plus beta equals v square, and then v would be the square root.
No, the magnitude of v, how long is v, is the square root of the sum of the squares. But the vector v algebraically is this length plus this length. It comes out here to a point. It gives you this vector. Right? not the same.
Okay.
No, this is an algebraic vector. This isn't the magnitude. This is the algebraic vector. It's not the magnitude of the vector. It
Right.
is the vector.
Got that now.
The length of that vector is the square root of the sum of the squares.
All right.
I understand. Okay. All right, this is going to be trivial, but if we have an algebraic vector, I have two algebraic vectors. V and W. When will V and W be equal? V and W are equal if and only if x1 equals x2 and y1 equals y2. Told you it was going to be trivial. Kind of disappointing, right? They put it in the book, so now I've put it in your head. You're welcome. I think that covers everything in this chapter, section 5.4. There's some example problems. I would encourage you to read through them and work through them and understand them, and you should be good to go for the homework assignment. Any questions? Is there anyone who did not sign in the sign-in sheet? Is there anyone who does not have anyone with homework to turn in? Anyone who did not get a take-home exam? There's that. And here, I got homework for you. Where is the sign-in?